Now, in this video, let us discuss. Let me introduce you with the concept with semiconductor materials and then with semiconductor devices. And to start with, the point is that solids we can in general talk about solids and they can be classified into into conductors and semiconductors. Now, within the domain of conductors, we can classify conductors. We can classify conductors as metals or semiconductors. So this will be the right choice to start with. Now we understand uh, uh, that that a semiconductor is an insulator. I mean, it is an insulator in which at room temperature some charge carriers are mobile. And they are mobile because of the thermal energies that they possess at room temperature. So if we talk about these semiconductors in general, we say that these materials they have conductivities, and there is a range of conductivities that these semiconductors possess. Uh, and in addition to that, I can say that suppose a semiconductor is an insulator in which at room temperature some charge carriers are mobile. That's what I'm trying to tell you. And at absolute zero, now if we talk about the temperature, if we talk about the temperature equal to something close to zero, uh, this semiconductor behaves as an insulator. It behaves absolutely as an insulator. Now, perfect crystals of most semiconductors would be behaving like insulators. Now, the only difference between semiconductors and insulators at absolute zero, at 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 0 Kelvin, at at 0 Kelvin, uh, lies it lies in the magnitude of the forbidden gap between the conduction band and the valence band. So to be very trivial here, if we have two bands, uh, one is valence band and another is conduction band, and uh, and what I'm trying to tell here is that the semiconductors and insulators, uh, the only difference they have at absolute 0 Kelvin is in terms of the magnitude of forbidden gap that they have. I mean, in case of suppose I talk about the semiconductors, this band gap is small. This band gap is small. They have small band gaps, and uh, in case of insulators, this band gap is large. So band gap is large for insulators. Now that's the point. Now, on the other hand, metals differ from semiconductors. Now they differ from semiconductors in several aspects, and the most fundamental and significant difference that we can talk about is that metals conduct electric current by means of negative charges. I mean metals, they conduct by virtue of uh, electrons. And when we talk about the semiconductors, here we have two types of charge carriers. One is electrons and another is holes. Now, electrons are positively charged particles, and holes, these are the vacancies. These are the positively charged vacancies that develop when electron leaves the site. So the site left at a place inside the semiconductor by convention has a positive charge, and this positive charge is termed as hole. So that's the case here. That in case of metals, we have electrons as charge carriers alone, and in case of semiconductors, we have uh, electrons as well as holes as charge carriers. Now, if I have to proceed from here, I would like to say that 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 if I have to classify these materials on the basis of some parameters, say for example, in terms of resistivity, in terms of resistivity, uh, if I talk about the metals, in case of metals, if we increase the temperature, if we increase the temperature, there are more collisions between electrons, and these collisions lead to increase in the resistivity of these metals, and this can have another explanation in terms of relaxation time. As the temperature increases, the relaxation time of uh, the metals increase sorry it decreases, and with the decrease in relaxation time, there is increase in the resistivity of the material. But that's not the case with the semiconductors. If we talk about semiconductors, with increase in temperature, here the story is different. What happens with the increase in temperature? You have more and more electrons available in the conduction band, and the availability of electrons in conduction band leads to increase in the conductivity of these materials. So, so here is a distinction between metals and semiconductors. And in general, if I talk about the resistivity of a semiconductor, if I talk about the resistivity of semiconductor at room temperature, at room temperature, it ranges between 10 to the power of minus 3 to 10 to the power of minus 6 ohm centimeter. And 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 uh, uh, and bet- this resistivity value that is here, on an average, I'll say that this value is at the middle between insulators, insulators, and and metals. Now, in case of metals, it's extremely large. This resistivity ranges from 10 to the power of 14 to 10 to the power of 22 centimeters. And in case of metals, certainly its value is less than that of uh, 10 to the power of minus 3 to 10 to the power of minus 6. So this is how in generality we can have a classification on the basis of some numbers, some parameters between a semiconductor, between a conductor and an insulator. Now, to be precise here is now the semiconductors that we have, we call them pure semiconductors. Now, these pure semiconductors are also called as they are also called as uh, intrinsic semiconductors. Intrinsic semiconductors. Now, uh, taking into the consideration all the physical characteristics of semiconductors, I mean, it is very difficult. It's very difficult to define a semiconductor because on the basis of electrical conductivity or resistivity, a semiconductor may be defined as a substance which has a resistivity, the range that I talked about in between conductors and insulators. But for the same material at absolute zero, at 0 Kelvin, the resistivity of most of the semiconductors approach to the resistivity of insulators. That means if you have a semiconductor, uh, and in most of the cases, the semiconductor behaves as insulator. They behave as insulators as you move towards 0 Kelvin temperature. So this is the case here. So defining a semiconductor in terms of its conductivity is not the absolute way of speaking about its about what semiconductor in reality is. Uh, if we proceed from here, we can see that in case of uh, these uh, these semiconductors. So what is happening here when you boil down the temperature to 0 Kelvin? In this case, the resistivity of this semiconductor is changing, and it's going up. It's going up as the temperature is increased. So the same material which is behaving as semiconductor is behaving as an insulator at absolute zero. So this is one of the important characteristic, and here we can understand that there is a relativistic nature in defining these materials, whom we call as semiconductors. So we have the examples of these semiconductors like germanium is a semiconductor, silicon is a semiconductor, and they are regarded as basic semiconductors. And in early solid state devices like p-n junctions uh, and transistors, okay, and transistors, germanium, it was exclusively used, but now it has been replaced. This germanium has been replaced by by silicon due to its availability in abundance. So silicon is abundantly available. So that way, uh, this germanium has been replaced in most of the devices, the most of the electronic devices. And if I talk about at present we have the complex integrated circuits, whom we call as ICs, and these are used these are not these are manufactured from this easily available material silicon, and in addition to the elemental semiconductors, some compound semiconductors are used, like these semiconductors. They fall like CDS, cadmium sulfide, gallium arsenide, lead sulfide, and so on. So here I have tried to give a brief introduction of these semiconductors, to get an idea of understanding what the semiconductors are, and it has become a reality that we cannot have a fixed definition for these semiconducting materials, because they behave differently under different circumstances. And now, talking about uh, the, 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 the characteristic properties of these semiconductors. If we talk about the properties of the general properties, so the general properties of semiconductors. Now, if we have to talk about it, the first important point I would like to say is that that semiconductors, they have negative temperature coefficient of resistance. Negative temperature coefficient of resistance. What does that mean? That means the resistivity of semiconductors decrease with the increase in the temperature, which is not the case in case of the metals. Now, the second important characteristic property is that semiconductors have high thermoelectric power, with signs both positive and negative relative uh, to a given metal. So they have very high thermoelectric power. This is important. High thermoelectric power. The next important property of semiconductors is that their electrical conductivity is very much affected. This is a very important point. It's very much affected by adding a small amount of impurity. Uh, and this addition of impurity that we add to these semiconductors, we call this thing as doping. So that means you are changing the character of this semiconductor. Wherever you want to take it, wherever your interests are, you add some state of impurity in the semiconductor, and it gives you the result in accordance with the doping that you have gone with. So, what is doping? Doping is it is the addition of small amounts of impurity to the semiconductor, right? The next important point would be it would be a junction. Suppose we have two types of semiconductors. One is called P type and N type. We'll be talking about them. Uh, when we have a when we have a P material that's formed as P material and N material, right? When this is the case, then uh, we can have the application of making devices based on the composites made of two different types of extrinsic semiconductors. And extrinsic, what I said, is when you add some doping to a pure semiconductor, we get a semiconductor which is called as extrinsic semiconductor, and we will be talking about that we will be discussing those things in future. But here I'm trying to tell you that what are the general properties of these semiconductors. So based on having materials like P type and N type, there are devices being brought in action, and these devices are used in technologies. The next important point is sensitivity. Now, this is important point, sensitivity. Sensitivity. To what? Sensitivity to light. Now, these materials, these semiconductors, they are affected by light. So either they can produce photovoltage, or they can change, their temperature can be changed. So you can have photovoltage, or, or there can be the variation in the temperature. So, so they are sensitive to light. So once they are sensitive, their applications are tremendous. Their applications are immeasurable. And the next important point here is that their resistivities, they nearly range from, in a typical sense, from 10 to the power of minus 5 to 10 to the power of 4 ohm meter. So these are some of the important general, these are not the characteristic properties, these are the general properties that are linked with these semiconductor materials.